So far in this series, we've predicted lockup from a dyno sheet, and separately we've imported a data log to read slip and gear changes off of a real pass. In this video, we'll do both at once. We'll predict the combo, and then we'll pull in the actual data log from the same car at the track and overlay them, so you can see in one chart exactly how close the prediction was to what the clutch really did. We'll go with the Camaro that we were using earlier. Here we'll see that we're using a 555 cubic inch motor with a tight 4-speed gearbox. We'll save that vehicle and we'll load it into the predictor. We'll enter the following parameters for the clutch. We'll use 0.3 spring preload, a spring rate of 165, 6 springs, and 34 grams of lever weight. Under advanced, we'll use a 13-degree lever angle, 3 discs, and disc diameter of 10.5 inches. In air temperature, we'll use 60 degrees. We'll use a barometric pressure of 29.88 and a humidity of 39. Now we'll import the following dyno sheet. We can see at 7,000 RPM, we have a max horsepower peak of 1,258 horsepower. We'll enter a shift point of 6,300 and run our prediction. We can see our lockup RPM was 5,682 RPM, based off this dyno sheet and clutch spec. Now, let's navigate to the track log and log a run that we can import our data log to. Expand more details. Down at the bottom, under Compare to Prediction, we can select which prediction we want to overlay on our chart. We'll also import a data log here from a Racepak or CSV trace. Click Save Run. Now, click View Run. Click Expand on the data log. Now read the slip line with me, because it tells the whole story of this pass. Off the line, we can see the clutch is slipping hard, at nearly 100%. It decays and the clutch takes hold at about 1 second, at 59-55 RPM. That's the real lockup, and that's when the clutch has fully coupled the engine to the drivetrain. Now watch what happens at each shift. Right at 1 to 2, the slip jumps back in at 11%, and then it's back down to 0 within 1/10 of a second. Same story at 2 to 3, and 3 to 4. A small bump, gone almost as fast as it showed up. That's completely normal, and it's real. This isn't sensor noise. The drivetrain gets a shock every time the next gear engages, and for a few hundredths of a second, the clutch pack momentarily gives a little before the clamp force reasserts itself and relocks. On a healthy setup, that's all it is. A quick blip that recovers fast every time. What you're watching for is whether it snaps back down immediately like ours does, or whether it lingers, climbs, or gets worse shift after shift. The second pattern would mean that the clutch doesn't have enough capacity to hold the gear. That's a real problem to chase, not a chart quirk. Now for the predicted versus measured RPM lockup. Click Edit on the data log. Scroll down to Measured Lockup RPM and enter the actual observed RPM lockup. For us, it was 59-55. Click Save Run. Now click View and expand again. Take a look at the engine RPM lines, not the slip line. This is a different thing from those shift blips we talked about. First gear stays entirely above our predicted line. That makes sense. It's a clean launch. But watch second gear, and third gear, and fourth gear. The flat predicted line actually passes through the real trace in every one of those. And there's simple math behind that, worth understanding, because you'll see it on every real log that you import, not just this one. Our lockup number is always an engine RPM. It's never a drive shaft RPM. While the clutch is locked, engine RPM equals drive shaft RPM times whatever gear you're in. Flip that around, and you get drive shaft RPM equals engine RPM divided by that gear ratio. Here's the key to reading this. The predicted lockup is a single number, so the app draws one flat line straight across. It's an engine RPM value, and it doesn't know or care about gears or time. Same with the measured line. The prediction called lockup at about 5,682. The car actually held on a little longer before locking, at 5,955. That's a gap of about 273 RPM, under a 5% difference. The app shows you the delta right in the summary. Take our actual predicted lockup number, for example, 5,682 RPM. If we take this number and divide it by the first gear ratio of 1.85, we get 3,071. If we look at this first gear slip and follow it all the way until 0% slip, we can see the drive shaft RPM lines up right around there at 3,217. If we take that same predicted lockup number and divide it by the second gear ratio of 1.44, we get 3,945. And if we go to where the clutch locks in second gear, we see that drive shaft RPM is about 3,707. Same thing with second to third, and same thing with third to fourth, although the gear ratio is a 1 here. So our lockup RPM is right around 5,682 RPM. That's 4 completely different drive shaft numbers, but it's the exact same engine RPM the whole time. One prediction viewed through 4 different gear ratios. And that's the honest comparison, not the prediction getting one gear and missing the others. There's one lockup, one predicted line, one measured line, and the gap between them is what tells you how well your model matched your combo. 273 RPM, just under 5% on this combo. That's a tight, trustworthy prediction, and it's what we'll use the scale factor for. To use the scale factor, remember your measured lockup RPM, ours is 5,955, and navigate back to the predictions page. Here we can take that measured lockup RPM of 5,955 and compute our scale factor. Now we can see our suggested scale factor is 1.048. We can apply and rerun. Our scale factor is applied and our lockup RPM dropped slightly. We'll use this to calibrate from an actual run and nudge the model's scale factor until its prediction lines up with what you actually see at the track. Do that once or twice for a given clutch, and the predictions for every setup after that will get sharper. For an additional alternate view of the data log, under Engine Dyno Sheet, we can import our logger here. Now, if we navigate back to the track log and view our shift points, we can take that engine RPM and enter them as shift points, then run the prediction. We now have charts that are split up to analyze specific measurements: engine versus clutch torque, engine versus clutch horsepower, and slip versus RPM. We can also enter the run log and get an alternate view to our data log. Here we have engine RPM and drive shaft RPM versus time, and below, clutch slip versus time. And that's the loop of having a prediction overlay a data log. The dyno sheet goes in, the prediction comes out, the data log goes in from the real pass, and an overlay tells you how honest that model was. Do this every time you log a run, and your predictions will only get better. That wraps up the series. Thanks for following along.